Okay, so today I'm going to talk to you guys about some of the enhancements that we made to TensorFlowOnSpark since we did this last year this time. So a quick review for those of you who may not be aware, TensorFlowOnSpark is a little library or framework that allows you to run your distributed TensorFlow applications on your Spark clusters. Last year when we did this, if I recall correctly, TensorFlow, I think, was version 1.0, so a lot of stuff has happened since then. So we get you access to your data sets that are sitting on your Spark clusters, and like I said, we open sourced last February. These are the goals that we had last year when we presented. We wanted to run distributed TensorFlow with as few code changes as possible. If you've played with TensorFlowOnSpark on our website, you'll kind of get an idea of what we require, and I'll also demo some, or not demo, I will show some of that. Part of the framework's goal was we wanted to be able to support as much of the existing TensorFlow functionality as possible. A lot of the other frameworks got in there and substituted runtimes or substituted operators, and so it was a very kind of mixed bag of what would work or not. And in our world, we wanted to be able to just follow along with every version of TensorFlow, pop it right in, and go. And then, like I said, we wanted to be able to integrate with your existing data pipelines. So if you happen to have Spark jobs and whatever workflow orchestration producing your input data sets, we wanted to be able to very quickly throw that into your training pipeline. And this last item in italicized is something that I added for this year, which is basically we want to be as lightweight as possible. We don't want to take over your world. We don't want to impose a lot of stuff into your existing environments. So again, to review, we have two primary modes for TensorFlowOnSpark. The first one is what we call input mode Spark. And what this is basically we have Spark read the RDDs and then pass the RDDs to your TensorFlow process, which is running on the executors. As you can see, there's a little extra hop there, so there will be a little bit of performance hit there. The good news is if you truly care about that performance hit, we have input mode TensorFlow. So what this does is it basically uses Spark to launch your TensorFlow nodes onto the Spark executors, and then it pretty much gets out of the way. So in this mode, your TensorFlow app is fully responsible for reading from HDFS. And last year when I did this, the recommended way was to use this TF reader and QRunner. And it was kind of a pain to use. Luckily, there is now a new nice TF Data API from the TensorFlow team. And again, because our framework is pretty lightweight, that works right out of the bat. Okay, this is a very high-level view of what it looked like to run a TensorFlowOnSpark cluster. We have a new class called Tof Cluster, a run method. You pass a bunch of arguments. From the map function here is basically your main function of your TensorFlow application. Your arguments from your command line, how many executors you have in your cluster, how many PS nodes you want to carve out of that set, whether or not you want to run TensorBoard or not, and then your input mode, whether it was TensorFlow or Spark. For the Spark mode, there's two other APIs we have here, train and inference, and you'll note the big thing here is that you can pass an RDD into this, and this is what feeds your RDD into your TensorFlow application. And then last but not least, an API to shut down. So what's new? So since last year, we have introduced an API that conforms to the Spark ML pipelines. So I'll dive into the details of that. We've also introduced a Scala Inferencing API. One of the things that we've heard from some of our customers is that sometimes you get a model from the public domain, from their data scientists, and your production pipeline is all in Scala, and you really don't want to introduce Python into your pipeline, so this is a way to do inferencing in Scala. The other one is support for the new TF Estimator Train and Evaluate API. I'll get into those details later, and failure recovery. So the ML pipeline API, like I said, conforms to what Spark has. So now we have an estimator and a model. They're just called TF Estimator and TF Model. The estimator is responsible for setting up your cluster, your TensorFlow cluster, and also for conducting your training. The model represents the TensorFlow checkpoint or save model on disk, and it allows you to do your model transform in Spark. We've also introduced a couple of helper APIs to ease a little bit of the coding here. So if you've ever tried to export a saved model in TensorFlow, you'll understand why there's now a TF node export saved model. And the DFUtil is literally a little helper class to help us go from TF record to data frames. Last but not least, we worked on a lot of this in collaborations with a small Databricks team. So thanks to Tim, Sue, and Philip for their participation. So this is what the TF Estimator API looks like. You create your estimator, you pass in your TensorFlow main function. Again, the args are present there, similar to the TF cluster. We allow for an optional export function. Again, when you're done training, you typically have a TensorFlow checkpoint, but we also allow you to potentially export to a saved model format right then and there. And then you'll see that a lot of the args that we had before are now exposed as ML params. So you can do whatever ML param builder style you like. And last but not least, when you invoke estimator fit, that's when everything gets to go and start training. So this will actually do the training in the TensorFlow cluster, and it will save your model as a checkpoint or save model to disk, and that model class that gets returned allows you to then go do a transform. So once again, this model class is backed by your TensorFlow model on disk. We have some ML params for setting things like the saved model tag, the signature definition key, things like that, which are kind of defined by the TensorFlow save model format. A couple interesting things here is we allow you to set an input mapping and an output mapping on this model. So if you remember, this is, let's imagine a checkpoint saved on disk. This allows you to map a data frame column, in this case image encoded, to a tensor in your model called JPEGs, and an output mapping of the logits tensor in your graph will get mapped to a data frame column called output. And as all models are, when you invoke transform, this is actually lazily evaluated. So nothing happens at that point. In the Spark world, magic happens when you invoke the action. That'll happen at the right JSON step. As part of this lazy evaluation, there is a limitation. The model that you store on disk and the model that we load here must fit in memory of a executor. So each executor will load the model actually in a singleton and then use that to do inferencing. So it'll be data parallel inferencing and not necessarily model parallel. Okay. Oh, sorry. And if you really have a large model that you really need to use, you can always revert back to the old RDD-based API where we stand up a full cluster with multiple PS nodes. Okay, so this is an example of the export save model call. The main thing we did here was to turn a bunch of boilerplate code in Python into a single API call with an object called signatures, a Python object. So this is very similar to what the saved model format looks like. The difference is if you look at inputs and outputs, that little X and that prediction, we will go do the magic of digging up those tensors in your graph of operations and then doing the right thing of exporting. There is a little bit of a nice advantage of this mapping, is that you can actually use other outputs of your model. So for instance, typical image recognition has a classification output tensor. You can potentially, if you wanted, cut that off, use a prior layer and export that to your, pull that out as your output. Okay, so again, DFTUtils, it helps us go back and forth between TF records and data frames. The main thing to kind of be aware of here is that the TF record format is very sparse. There's basically only really 3 data types, and specifically the string and binary types are represented as bytes lists. So we have an argument here to help us infer the type. Okay. A little bit more about the conversions that we allow. So going from left to right, Spark has much richer data types, but those will all get flattened into the TF record base types, which are just float list, int64 list, and bytes list. If you go the other way from TF record to Spark, the items in bold are the ones that we will default to. If you don't provide a hint, that's what you'll get out on the Spark side. Okay, so next, we recently added Scala Inference API, as I mentioned before. Trick here is, again, it is for inferencing only. And part of the reason of that is because we are leveraging the TensorFlow Java API. And if you've read the documentation, you'll see the big word in bold, experimental. And so it's only really supported for inferencing. It's not really intended for training. And it's a little bit of a use at your own risk per the TensorFlow team. The way that this API works, again, if you've exported a saved model to disk, we follow a similar pattern with the ML Pipelines API, except this time there is no TF estimator. You don't get to train in Scala, but you can do inferencing. So this TF model, you point it at your saved model on disk, and you can do many of the same things. And we provide a similar DFUtil here. So this is an example of running an inferencing job in Spark using this API. So typical Spark submit, we reference the inference class, provide the jar. Currently the jar is just download the Git and compile for yourself. It's fairly lightweight, so it shouldn't give you too many complaints. If there's enough demand, we will obviously consider maybe throwing it up in a Maven repository or something. The arguments are, again, fairly standard. The one trick here is the schema hint. So here, because of all the type inferencing going on, we allow you to provide a schema hint, and this particular format is actually the Spark data type simple string. Because I didn't want to deal with struct types everywhere and trying to represent them on a command line. So if you provide these hints, the type inferencing will respect that as much as they can. Again, you provide the input and output mappings and where to put your predictions. Okay, so next, TF train and estimate. If you've not already come across this, this is the quote from the TensorFlow website. The key bit is it allows you to use the same code in a single node, say Python instance on your laptop, and then turn around the very next day, use the same code in a distributed environment. Obviously, we tweak it. Sorry about that. Obviously, we tweak it a little bit for TensorFlowOnSpark, but as I'll show you, it doesn't change too much. There's this little caveat sentence on the bottom. I wouldn't worry about it too much, but I wanted to throw it up there in case it mattered to you. Most distributed TensorFlow is between graph replication anyways. Okay, so what does train and evaluate buy you? If you've ever converted a single node TensorFlow application to distributed in the past, you would have had to instantiate a TF train server. You would have had some code, some boilerplate that said if PS worker. You would have had to create a supervisor or a monitored training session, and then you'd do a bunch of session runs. That goes away with train and evaluate, and especially with the TF Estimator API. And part of the reason why this works is they now take a lot of the cluster spec information that was formerly passed into your Python application, and they require it to be set as an environment variable. So each node will have the environment variable set to the full cluster spec, along with which node it's playing, which role it's playing. Something that comes along with this is now we require a master node. So there's a new optional argument in the TF run to supply a master node. If we see this, TensorFlowOnSpark will figure out and set the TF config on all your executors as required. So I know you can't read this. Don't worry, I will explain it. So the big blue blob in the bottom right is mostly boilerplate to convert a TensorFlow app to a PySpark TensorFlowOnSpark app. A bunch of imports and a bunch of argparse to get you nice arguments. And then at the very last two lines is your TF cluster run and your TF cluster shutdown. The first change at the top is basically just adding the context object. We require that so we can pass some useful bits over to your executor. The next two little lines are just me converting constants to nice arguments, just because this is what I needed when I was playing with it. And then the next two gray-blue blobs is me commenting out specific calls to TF Estimator train and TF Estimator evaluate. If you use these separate calls, you don't get the magic of the train and evaluate API. So that's all that that does. So on the whole, not a lot was required to convert this TF Estimator to fully distributed on TensorFlowOnSpark. Okay, so next up, we're going to talk a little bit about failure recovery. If you've played with any of this, TensorFlowOnSpark and TensorFlow, you'll understand that failure modes can be a little tricky. So first, a couple guiding goals for us as we were building this thing out. The main goal was that we wanted to surface the errors as soon as possible up to the Spark layer so that Spark and or Yarn and or whatever Spark is running on could try and handle those errors. First, from a task, per task way. If you're in Spark mode, that would just be a single partition of your data possibly failed, maybe it can get retried. If you're in input mode TensorFlow, it could be that your maybe your TensorFlow application had some kind of transient error, and if it is transient enough that it can be restarted by Spark and recover, then this would work. If it's not a transient error, then you eventually end up with a job failure. So Spark would eventually fail the job in the application, and we hope that some higher level orchestration above Spark would handle the retry of your Spark application. And if you set up your TensorFlow training to save checkpoints correctly early and often, then that retry would presumably restart from the last checkpoint. So with that set in mind, here are some of the things we changed or fixed. First, in Spark mode last year, TensorFlow exceptions were happening in the background task. The foreground task was your feeding. The background task was your TensorFlow. If there was a failure there, it kind of looked like a hang. So now we surface that out so that your job will fail, so that at least you can see that, hey, you had a shape mismatch error in your tensors. The next one is a reservation timeout. So we crossed this a couple times in the past, and basically what happens here is when we construct your TensorFlow nodes on top of the executors, a lot of times you get the executors, but for whatever reason, TensorFlow isn't fully coming up to speed, or we're not fully able to respond and construct the network. These first two were actually contributed by Eric on our team, so just wanted to call him out for those two because they're very useful. Next one, GPU allocation hang. A lot of times, because we are using, at this current moment, memory as a proxy for a GPU in our system, there's a good chance that you could get allocated to a GPU node, and for whatever reason, there are no GPUs available, mostly because people are not using memory as a proxy. And in this case, right now, we will actually exit you out so that you at least get to retry your allocation. There's also a cluster size mismatch that we hit quite a lot. This one is due to the fact that our architecture requires you to have the same number of executors as your expected TensorFlow cluster. So if you have 1,000 executors and you want to start a TensorFlow node of 3, that doesn't work. So we've added some handling to try and catch that condition and at least report you a nice error message. But there's still no dynamic TensorFlow clusters. TensorFlow code currently assumes that your cluster spec is set. The way that it's done in most cases is through virtualized hosts, IPs, and ports. And in Spark and then Hadoop, we don't have that yet. Okay, so I separated these out. These are also new, but the difference here is that we were able to support new TensorFlow APIs without any change to TensorFlow and Spark. All we did was give you an example of how to use it. So when TF data and datasets came out, we provided an example that uses input mode TensorFlow. This basically just does what you would expect. Spark gets out of the way. TensorFlow uses TF data to read directly from HDFS. For Spark mode, the only change to the code was that we, instead of using a normal dataset, we use dataset from generator, which is also provided in TF data. And that generator literally just takes the items off of our data feed that previously would have gone into a feed dictionary. Karis was very interesting as well. When Karis first came out, it was in TF contrib of TensorFlow. And when we first tried to support Karis, there were a couple very strange things that we had to figure out. We had to do this funny call to k.session. We still had to do fit or fit generator. That's not too bad. But the last one was that Karis generally like to save in an HDF5 format, which isn't supported on HDFS. And so we had to do a weird workaround with a Lambda callback in Karis. The good news is now Karis is in part of TensorFlow core. There's a nice API that converts it from a Karis model to an estimator, a TF estimator. And when you do that, you get basically a TF estimator that you constructed using Keras APIs. You get to use TF data, you get to use train and evaluate, which is very nice. So, where are we going from here? So the big news, or the big thing that we're kind of keeping an eye on is Hadoop 3.0. Two of the nice features, obviously GPU scheduling is one big one. Once we get actual GPU scheduling, hopefully a lot of the GPU allocation errors go away because we'll get formal GPUs as opposed to proxies of GPUs. And then the next big thing will be support for Docker containers. And this should help us avoid shipping around Python zip files with dependencies or versions of TensorFlow. So hopefully you can package that all up in different containers and support multiple all at once. And as always, I am still keeping an eye out for dynamic cluster management. One day this will work. And then it will allow us to basically have a node fail, an executor node fail, and hopefully that would get restarted by yarn and magically come up. But for now, retry at a higher level. So, in summary, TensorFlowOnSpark continues to evolve to support additional use cases and APIs. Most of the times we can support these new functionality with no changes to our core. This happens quite a lot. I upgrade TensorFlow versions and everything still works. And last but not least, lets you run distributed TensorFlow applications, both training and inferencing on your existing Spark infrastructure. thanks to Yahoo and Oaf for supporting us, or letting us work on this. And thanks for TensorFlow, Spark, and Hadoop for building awesome software that we just stitched together. And thanks to our open source contributors. Any questions?
All right, thank you, Lee. We have a mic up here for questions. So if you have a question, please come up to this mic right here.
Very nice presentation. Thank you. I was curious, and it's very good to have the Scala model, the Spark Scala model for getting predictions. Well, actually, inference. How would you recommend going about the reverse, like the estimator, or have the ability in a Scala stack, Scala Spark stack, to be able to train TensorFlow models? Like,
yeah.
What would be the best way, in your opinion, to train in that kind of stack?
Yeah, that's kind of difficult because, again, we're relying on TensorFlow's ability to support other languages. And right now, as far as we're concerned, TensorFlow's primary training language is Python, unfortunately. And so if it... Sorry. A Python stack running in Scala? Sorry.
If you have, suppose I have a Python spec with all the, the training, the network, everything there in a Python. I'm okay with putting a Python, but then in a Scala stack, how would you go about, parallelizing that?
Yeah, so that was, I think, the Scala API. Basically, you would train in Python, build a saved model, have it stored on disk, and then you can actually instantiate a Scala TF model pointing to that saved model. And then you can do parallel inferencing times 100, 1,000, whatever. Okay?
Hi, thank you for the presentation. So you mentioned Keras Estimator too. Is that also a valid stage in the Spark pipeline? So it's basically the same as just TF Estimator? Can I put it in a stage in a pipeline?
Can you put it in a stage of a ML pipeline?
Yep.
Okay. That's an interesting question. I don't know if I've tried that per se. I will need to try that and get back to you.
But TF Estimator I can, right?
The only reason I kind of hesitate is because I think it should work. It should work.
Okay.
Because the ML pipelines, really all it does is at training phase, it literally starts a TensorFlowOnSpark cluster. So it looks very similar. The only difference is instead of RDD, we take a data frame. But the actual TensorFlow code just executes. So it should work. If it doesn't, we can patch it, I think.
Okay, and if we do that, if we have a pipeline that one part is, this TF Estimator, and we save it, does it follow the same, basically, folder pattern that pipelines have?
What folder pattern?
Like when you do some pipeline that's save in ML pipeline world, you have just like different, each stage is a different folder. Like I'm wondering if one of those folders
I think this would just be modeled as one of those stages. Like
Okay.
if you use the ML pipeline API, generally you would have other things in front, transformers, whatever. Those would probably have to save in whatever data structure path that you wanted.
Okay.
But this is literally just kind of like a train step or train phase of the pipeline.
Okay, cool.
Last year, you guys did a good effort and got good results on improving the distributed nature performance of the TensorFlow. Do you have any update on that this year? Have you guys considered, although this a new ring or reduce pattern, which seems to be promising?
Are you referencing the performance measurements and the nice graphs we drew with InfiniBand and also Inception?
I think you guys did RDMA.
RDMA, yeah. So RDMA is actually now part of core TensorFlow. It got pulled into TensorFlow itself. So whatever performance there, it's actually evolved quite a bit beyond when we first released it. And then in terms of performance, it's mostly based on how much the TensorFlow performance has changed. Because like I said, we're pretty lightweight. We try and not replace the runtime. We use the runtime. Okay. So if TensorFlow comes out and improves speed by 2x, we would get that improvement. Okay.
All right, if that's the last of the questions, let's have one more round of applause for our speaker.